I've spent most of my life studying physics, and yet I've recently realized I had a huge misconception. I used to think that every object in the universe has a single trajectory, a single path it follows through space. A ball thrown across a field, it moves in one curve. Light shining through a window, it travels in a straight line. Simple, predictable. That was my intuition. But as I delved deeper into quantum mechanics, I realized something far more astonishing. Nothing actually takes just one path. Instead, everything, light, electrons, protons, even you and me, is exploring all possible paths simultaneously. And the trajectory we see is just the path that survives a delicate dance of interference. Let me take you through a simple analogy first. Imagine you're on a beach, and you see your friend struggling in the water. You want to get to them as quickly as possible. Naturally, your first thought is to swim straight to them. That's the shortest distance. But there's a catch. You can run much faster than you can swim. So maybe running along the shoreline and entering the water closer to your friend is a faster option. But now the total distance is longer. There's a trade-off between running and swimming. The optimal path is somewhere in between, depending on your running speed and swimming speed. Now, here's the surprising twist. The same logic applies to light. Light doesn't know where it's going in the way we do. There's no brain calculating the fastest route. Yet when light passes from one medium to another, say from air into water, it takes the path that minimizes travel time. This is called Fermat's principle, or the principle of least time. It turns out that the rules of classical physics are just the result of a deeper, more fundamental principle, the principle of least action. Historically, this concept emerged from studies that seemed unrelated to particles or trajectories at all. At the end of the 19th century, Germany was electrifying its cities. Street lamps powered by gas were being replaced with electric bulbs. Scientists were curious. How can we maximize the amount of visible light emitted by a hot filament? They studied materials that glowed when heated, black bodies, and discovered that the intensity of radiation emitted depended on temperature. At low temperatures, different materials emitted light differently, but at higher temperatures they all seemed to follow the same pattern. The classical physics predictions were almost correct, but at short wavelengths they went catastrophically wrong. According to the math, a black body should emit infinite energy at short wavelengths, obviously impossible. This problem became known as the ultraviolet catastrophe. Enter Max Planck, a physicist who, by his own admission, initially approached the problem reluctantly. He almost gave up on physics as a teenager, because his professor told him the field was essentially complete, but Planck persisted. He tried everything to reconcile theory with experiment, until one day, in an act of desperation, he proposed that energy could not vary continuously. Instead, energy came in discrete packets or quanta proportional to the frequency of radiation. E equals sine HF, E equals sine HF, where HHH is now known as Planck's constant. Planck's breakthrough solved the ultraviolet catastrophe, but even he didn't fully understand why it worked. To him, it was a formal trick, a mathematical solution without a physical interpretation. That interpretation would come from Albert Einstein, who showed that light itself comes in discrete photons, each carrying energy h. Using this idea, Einstein explained the photoelectric effect. Light only ejects electrons from metal if it has a high enough frequency. Suddenly, light could not simply be a continuous wave, it also had particle-like properties. This duality became one of the cornerstones of quantum mechanics. Soon after, Niels Bohr tackled the problem of atomic structure. Classical physics suggested that electrons orbiting a positively charged nucleus would radiate energy constantly and spiral inward, collapsing the atom. But atoms are stable. Bohr postulated that electrons could only occupy orbits where their angular momentum was quantized in units of La each bar b, chi bar equals sine h2 pi, chi bar b. At first, this quantization seemed ad hoc. There was no reason why nature should limit angular momentum in discrete units, and yet it worked perfectly to explain the spectral lines of hydrogen. A few years later, Louis de Broglie proposed something extraordinary. If light can behave as both a wave and a particle, maybe matter can too. He suggested that all particles have an associated wavelength, given by Ley hp Lyman equals sine hp Lyman equals sine hp, where pp is momentum. Electrons around a nucleus could only exist as standing waves. This explained Bohr's quantization. Naturally, only orbits where a whole number of wavelengths fit around the nucleus were stable. At this point, something remarkable emerges. Waves are not confined to a single path. If an electron behaves like a wave, then in principle, it must explore all possible paths between 2 points. This is where my original misconception that particles follow one definite trajectory completely falls apart. Even the double slit experiment, which I had taught countless times, illustrates this vividly. Fire electrons one at a time through two slits, they hit a screen and form an interference pattern. Each electron seems to interfere with itself. How? Because it's not traveling through just one slit, it's effectively taking both paths simultaneously. Richard Feynman captured this idea elegantly with what we now call the path integral formulation of quantum mechanics. According to Feynman, a particle moving from point A to point B doesn't choose a single path. Instead, it takes every possible path. Some paths are straightforward and familiar. Others might loop wildly, even theoretically faster than light, or take a detour to the moon and back. Mathematically, we assign a complex amplitude to each path. When we sum them up, most paths cancel out due to destructive interference. Only paths near the path of least action survive and dominate the behavior we observe. Action, in classical mechanics, is a quantity defined as the integral over time of kinetic energy minus potential energy, S SORN T V dt. In quantum mechanics, action determines the phase of each path. For everyday objects, actions are enormous compared to Planck's constant, so the phases of almost all possible paths spin around wildly and cancel each other. This is why macroscopic objects appear to have a single well-defined trajectory. For electrons and photons, actions are tiny, so more paths contribute, leading to quantum effects like interference and diffraction. Even light, which seems to travel in a straight line, is constantly exploring countless paths. Our classical intuition is just the result of constructive interference along the path of least action. This principle explains why light refracts, reflects, and why a thrown ball follows a parabolic trajectory. Everything in the universe, from planets orbiting the sun to particles in a collider, is governed by this sum over paths principle. It's the hidden rule underlying all motion, quietly orchestrating reality in a way that classical physics can only approximate. In essence, quantum mechanics reveals that what we perceive as a single deterministic path is just the tip of a vast ocean of possibilities. The universe doesn't choose a path, it simply allows interference to select the paths we observe. And at the heart of this selection process lies the concept of action, a subtle, profound quantity that governs everything from the glow of a filament to the motion of the stars. Feynman's path integral and the reality of all possible paths. So far, we've seen how quantum mechanics revolutionized our understanding of nature, from Planck's quanta to de Broglie's waves. But let's now dive deeper into Feynman's radical insight, the idea that every particle, every photon, every electron explores all possible paths at once. This concept isn't just abstract math, it can actually be demonstrated in the lab, and it fundamentally changes how we think about motion. Imagine you're firing a particle from point A to point B. In classical physics, it travels along a single predictable trajectory. In Feynman's view, it doesn't. Instead, it simultaneously explores an infinite number of trajectories, some straight, some wildly curved, some looping back on themselves. How do we make sense of this infinite chaos? The answer lies in something called the amplitude. Every path is assigned a complex number, a little arrow pointing in a direction determined by the phase of that path. When we add up all these arrows, most of them point in random directions and cancel out a process called destructive interference. Only the arrows corresponding to paths near the least action align and reinforce each other, constructive interference. And those are the paths we observe in the real world. To understand this better, let's return to light. We see light traveling in straight lines, reflecting off mirrors at equal angles, bending through glass, following predictable rules. But Feynman showed that these behaviors emerge from the sum over all possible paths. Light doesn't decide to follow a straight line. It takes every possible route, including the weird ones that curve, zigzag, and even go backward in time. The reason we only see straight line reflection is that the phases of all the other paths cancel out, leaving the path of least action as the dominant one. This principle can be demonstrated experimentally using mirrors, lasers, and diffraction. Suppose we shine a laser at a flat mirror. According to classical physics, the light reflects in one spot. But now imagine we break the mirror into tiny strips and block parts of it. The result is astonishing. The reflected light pattern spreads into multiple spots. Why? Because we've removed some of the paths that were canceling each other. What we see now is the interference of the remaining paths, literally evidence that light was exploring all possibilities, even the crazy ones we normally don't see. When we remove the blocks, the paths cancel again, and the familiar reflection reappears. This is not just a demonstration, it's a visual proof of the path integral in action. Mathematically, the phase of each path is determined by the action along that path divided by Planck's constant Held par. The action itself is an integral over time of the kinetic energy minus the potential energy, S, or TdV dTs equals sign in TdV dTs. If particle moves, the phase of its amplitude winds according to this action. For macroscopic objects, the action is enormous compared to El Porto, so even tiny deviations in the path cause the phase to spin wildly. When you sum over these paths, nearly all of them cancel out. That's why a thrown baseball follows a single parabolic trajectory. For electrons, photons, and other microscopic particles, the action is small. So many paths contribute, leading to the rich interference effects we observe in quantum experiments. This approach fundamentally unifies classical and quantum mechanics. Classical mechanics, with its predictable trajectories and deterministic laws, is just the emergent behavior of the interference of many paths. Quantum mechanics, on the other hand, reveals the full complexity beneath the surface. Every motion is a superposition of countless possibilities weighted by their action. In other words, classical reality is just the tip of the quantum iceberg. Feynman's formulation also gives us an intuitive way to understand why nature seems to optimize itself. Take light refracting through water. Classical intuition says it chooses the fastest path. Feynman's approach shows that the light isn't making a choice at all. Every path contributes an amplitude. Paths that would take longer than the least action path interfere destructively. Paths close to the least action path interfere destructively. The result? The path of least action naturally emerges without the need for foresight or optimization. Nature doesn't plan. Interference does the work. To illustrate this further, consider the famous double-slit experiment. Electrons are fired one at a time through two narrow slits, then detected on a screen. If electrons were classical particles, we would see two bands corresponding to the slits. Instead, we see an interference pattern, a signature of waves. Each electron behaves as if it went through both slits simultaneously, interfering with itself. Feynman's insight generalizes this. The electron explores all possible trajectories from the source to the screen, not just the two obvious ones through the slits. The probability of detecting the electron at a given point comes from summing the amplitudes of all paths. Paths that interfere constructively dominate, producing the familiar interference fringes. Even macroscopic phenomena, light reflecting off a mirror, planets orbiting the sun, a baseball flying through the air, can be understood this way. The principle of least action governs them all. A planet doesn't know the shape of its orbit. It just follows paths whose action is stationary. The interference of nearby paths effectively cancels all the other possibilities. This is why Newtonian mechanics, with its predictable laws, works so well for everyday objects, even though, at a fundamental level, those objects are still exploring an infinite number of paths. The more I reflect on this, the more profound it becomes. Classical physics, quantum mechanics, special relativity, and even field theories can all be expressed in terms of a Lagrangian, a function whose integral gives the action. Write down the correct Lagrangian, and the laws of physics emerge naturally. The hunt for a theory of everything, the ultimate unifying framework of physics, is essentially a search for the Lagrangian that governs the universe. Every interaction, every force, every particle behavior flows from it. It's the ultimate simplicity underlying apparent complexity. And yet, this is more than just mathematics. Feynman's path integral gives a glimpse into the true nature of reality. The universe is not deterministic in the classical sense. It is a vast, probabilistic network of possibilities. Each particle, each photon, each quantum system is a superposition of countless paths, with the classical world emerging from interference. It's a universe where every potential path exists simultaneously, and what we perceive as reality is the outcome of their intricate interference. We can even see this with light experiments. Shining a laser at a mirror with tiny slits or obstacles allows us to witness hidden paths. The light doesn't bend around these obstacles, it explores every trajectory. Some paths cancel, others combine, and the resulting pattern is exactly what quantum mechanics predicts. These demonstrations aren't just theoretical, they make visible the astonishing fact that nature is inherently probabilistic and holistic. Finally, the principle of least action teaches a deeper lesson. Reality is emergent. The laws of classical physics, the orbits of planets, the paths of balls, and even light's predictable reflection are all consequences of interference patterns at the quantum level. Quantum mechanics isn't a bizarre exception to the rules. It is the foundation upon which those rules are built. Every trajectory we see is a survivor in a vast sea of possibilities, a manifestation of constructive interference amid the chaos of paths that nearly all cancel. So the next time you watch a ball fly through the air or see light reflect off a surface, remember this: what seems simple and deterministic is actually the result of an astonishingly complex and elegant quantum computation happening at every moment. The universe is exploring every possible path at once, and what we call reality is just the elegant pattern that emerges from this infinite web of possibilities. The principle of least action is not just a rule, it's the hidden rhythm of nature itself.